I'd like to introduce our speaker today, Andrew Basilio from Columbia. Andrew Basilio is currently a fourth-year PhD candidate in biomedical engineering at Columbia University. He also completed his BS and MS in bioengineering at UCSD. Between completion of these two degrees, he worked at Illumina as a systems engineer. In his free time, he likes to surf, play piano, lift weights at the gym, and do martial arts, including Taekwondo, karate, and Brazilian Jiu-Jitsu. He also enjoys the outdoors, especially camping with friends and deep sea fishing with friends as well. Once again, please remember to keep your video and audio off for the duration of the talk and save any questions that you have for the last portion of this webinar, or we'll have an opportunity for all attendees to ask questions to Andrew. And without further ado, we'd like to hand it off to Andrew and take it away.
All right, sounds good. What's up, everyone? So I'm going to share my screen right now. Hopefully, I think, can someone put the setting where I can share it? I was able to last time, but now I can't.
Sorry, Andrew, 1 second. I'll stop sharing and you'll be able to share.
Alrighty. All right, everyone. So I will start. So there's a pretty wide variety of people who are watching this right now. So there's people in high school I know of, people who have just graduated, people in graduate school, people who are kids. So I'm going to try to address this talk towards everyone in addition to the work that I've been doing, just to see, if anyone's, been interested in what kind of work I've been doing, and to, try to give tips to anyone who's been looking to transition from undergrad to finding a job, or whether they're trying to find internships, or if people are trying to go back to graduate school after working for a little bit. So I really hope that this talk is valuable to all of you guys. So the contents of this, I'm just going to be a very brief about me section, why I chose engineering, specifically biomedical engineering. My high school experience, such as courses in high school, my undergrad experience, then my experience working in industry, and then some tips and tricks that I found out that work for applying for jobs. They work. I got in a bunch of jobs. And master's experience and my PhD experience, as well as applying for grad schools. So yeah, real quick, just a very brief timeline. Went to Walnut High School. After Walnut High School, I went to UCSD and I did my BS degree in bioengineering. After that, I worked for about 1.5 years at Illumina, which is headquartered in San Diego. Get rid of that UCSD right there, as a systems engineer. Then I went back to UCSD, literally 2 miles away, and I did my master's in bioengineering. My focus on my master's is more systems biology related. So all of my work has been computational during my master's. And then right now I'm doing my PhD at Columbia. I'm currently a 4th-year PhD candidate, and my work is also computational so far, and I'll go into detail on those. Not too much detail because there's crazy math in there, and I don't want to throw all the math out there. So real quick, I just want to put out there that my life path was not linear. I think a lot of people think that, to like climb up there and to be effective in your field, you have to have an idea of what you want to do from a young age. So basically, like starting at, once I graduate high school, I need to know what I'm doing, right? For me, I honestly had no clear vision until like a few years ago. So if anyone is like feeling discouragement about like, I have no idea what I need to do next, I would just say like a word of advice, just do the next best thing in the moment, like in the context of the moment you have. And so, yeah, I'll go through my journey. So why did I choose bioengineering? So first of all, I was interested in science since I was young. My parents, they both work at JPL, so they obviously talked about engineering, aerospace, space, and all that stuff. Originally, I wanted to become a medical doctor. So I wanted to be a physician, and bioengineering was a good option because it completed the med school prerequisite classes. And also, if I decided to not pursue that path, bioengineering was the perfect option because it had a bunch of other career options. For example, I know people in my class who went to law school, dental school, or did something completely different, investment banking. I also like bioengineering because literally I feel like I studied almost every STEM subject out there. Just, from the coursework, you can see here briefly biochemistry, linear circuits, organic chemistry, fluid mechanics, triphasic biomechanics, C++ programming, neurobiology, continuum mechanics. Yeah, vector calc. It's just a lot of different classes. For me, what I found beautiful about studying all of this is seeing how they were all connected. So seeing all the computer science being connected to molecular biology, being connected to linear algebra, vector calculus, and just, seeing how all of it came together in my head, it was really beautiful. And that happened maybe around third year when I was taking upper div classes. And it was a very eye-opening experience. So because there are people who are like, in high school or college in this talk who, are probably not sure what they want to study, I would say the first thing you want to prioritize is choose a major that you're truly interested in. Because if you pick a major you're not interested in, it's going to be a chore. You're not going to like it. Second priority, I would almost put it up to the first one though, is to choose a major that can give you a wide variety of options after graduation. That's just because, people's likes and, perspectives can change over time. So I think that it's really important to have a major that's also flexible. But if you really know what you want to study, choose that. So high school, I was involved in the AP and IB program, took the highest level of math courses, biology, chemistry courses, also German. I know a little bit of German. I took no physics courses though, and that was my downfall because the first physics class I took at UCSD, I got a C. And then after that, it went up. But in the beginning, it was not good. So what you can do is challenge yourself to, in high school, if you're interested in doing STEM subjects. So for example, science or engineering, any of that, take the highest math, chemistry, physics, biology, computer science classes you can in your high school. I would say that, even though you're not sure what to do, and even if you're leaning towards more humanities and not towards STEM, at least you're training yourself to stay diligent and focused on your work. So my undergrad experience. So I was in the bioengineering pre-medical track at UCSD. This track actually doesn't exist anymore at UCSD, so it's been replaced. And during my undergrad, I was involved in 3 internships. So I did an internship at the Oakcrest Institute of Science. And this was where I was working on delayed drug delivery. So basically, if people forget to take their tablets every evening for 30 days straight, that's actually, it's hard for people to remember to take their pills. So what I did there was try to develop a polymer and test a polymer degradation that would release drugs at a predictable rate. Next, I did work at the UCSD Biophotonics Laboratory. So this bottom picture is from a page there. Pretty cool because lasers, they're photons. Photons have energy and therefore they have momentum. So with lasers, you're actually able to impart a force on an object. And you're able to, for me, I was able to cut the nuclei of these cells. I was actually able to use lasers to activate a sorrelin agent that would cause double strand breaks and different types of DNA damage in cell nuclei. And then I would study how repair proteins would go to that site of damage and try to, repair that damage. The goal of this was to try to address different diseases like Fanconi anemia, I believe that was a disease, and different types of cancers. My last internship, my third one in undergrad, was at the La Jolla Bioengineering Institute, where I studied traumatic brain injury. So most of it was just mechanical design and fabrication and planning, creating like a solid structure to induce shockwave injury into rats. And the goal of this was to study traumatic brain injury. So you can see that my experiences were very broad. I honestly wasn't sure what I wanted to do. I just took the next best thing. So for people who are in undergrad right now, I would say first year, focus on adjusting and doing well in courses because college is really hard, especially coming from high school. During your second year to fourth year, ideally you want to maintain your good grades and get involved in internships. And for people who are, for example, like in engineering, I would highly recommend you do get an internship. Oh, it's blocked by the picture, but do an internship ideally at the end of your third year in that summer, because a lot of times the company where you do your third year internship will take you after you graduate your fourth year. I've seen that so many times, and that's like a really good way to get a job afterwards. And also make sure to apply for summer internships several months in advance. So next, I'll talk about my experience in industry. So after undergrad, I decided not to apply for medical school. For me, the experience, you know, like when I was shadowing the physicians, it was a great job. But for me, I knew I was more interested in creating and innovating medicine. So physicians, extremely useful, but they diagnose, treat patients, and interact with them. For me, I really wanted to keep with the technological, or like the, you know, the technicalities of physics, chemistry, mathematics, to design and create tools and like models or new medicines that could impact medicine. So I was accepted to several engineering positions in several major companies. I only applied in San Diego, and I chose Illumina. So what you see here is just a sequencer, a DNA sequencer from Illumina. I didn't work on that. That's just for decoration. So yeah, I was a systems engineer. I did hardware and software troubleshooting. I also worked on thermal systems, optics, and circuits, and I collaborated with different departments to troubleshoot instrument failures. So just as a recap, I will dive into my work. I'm just trying to address, you know, everyone, because this is such a vast crowd. So some tips for applying for jobs after graduation, I would say start applying during your fourth year. Like I would say even at the beginning of your fourth year, or even January of when you're going to graduate. Treat the application like application process like a full-time job. So if you're unemployed, you know, use 8 hours a day to tailor your resumes and to start applying to jobs. Move fast and be biased towards action instead of being wishy-washy, because I noticed that when I was experiencing that, like, oh, I'm trying to be perfect, I don't know if I should do this, I wouldn't send any resumes. So action is better. Also go to the University Career Services Center and get resume advice. They honestly help so much, and they help me a lot too. Another important point is to tailor every resume for each position. So don't just send a wide variety out there. They know if you put in the time and effort to tailor your resume towards their job. And make sure that you emphasize the classes you've taken and the skills you've learned even during your lab courses. So for example, if you're a biochemistry major, you know, an undergrad, or a biology major, you're going to study like DNA recombinant techniques. Or if you're an engineer, you're going to take engineering lab courses or physics labs. Put in those skills in your resume, and, you know, like, don't just think that it has to, the skills you put in there have to come from a job or a research position. Also make a LinkedIn profile. That's how I got my Illumina position. Someone found me. So LinkedIn works. Network and apply through different routes. So Craigslist, yes. I got into Hologic GenProbe and I think another company with Craigslist. So, you know, you're trying to stand out from other applicants. So you got to do something different from them, you know, whether that means going to career fairs and you don't have time to talk to everyone, just drop your resume in the pile or use a different color resume paper. Tips and tricks, it works. So so when I applied for graduate school, so I applied for the master's after Illumina. And one thing I want you guys to realize is that if you decide to do a PhD, it's not necessary to do a master's first. Some schools you have to, like at Columbia, you need to do a master's first. You also need recommendations, so you can get that from work supervisors and professors. So for people who are in undergrad right now or who are in industry and want to go back to do a master's, you know, have a clear reason why you want to further your education and see if a master's actually gives you an advantage for accelerating your career. Sometimes it's not even necessary. Honestly, a master's is pretty quick, 1 to 2 years, and it's not too big of a decision. So, I don't think it's too bad to step away from the workforce to do that. So here's the reason why I wanted to do a master's after graduating. So for people who have been considering doing a master's, it seemed that most people at Illumina who are in higher career positions, they had advanced degrees. That's not always the case, but there's definitely a statistical significance where I was like, okay, these people look like they have at least a master's. Also, it can boost the application if I decided to pursue a PhD, and it can help me apply for higher positions if I go back to industry. So to me, I thought I had nothing to lose. So in my master's, I completed master's level coursework and I conducted research for a year, and then I wrote a thesis. So now I'm going to dive into the work that I did for my master's. So basically, what you're seeing here is a picture of photosynthesis. So some people are like, okay, why are you studying plants? What is the purpose of this? So as you remember, if I mentioned before that my work was in systems biology, which is up here. So systems biology, you can think of it as, when you look at the world around you, how people interact, how animals interact with their environment, different ecosystems. It's very complicated. It's a system. What you see in this picture is, a molecular pathway for electrons that go through the photosynthesis molecular pathway. However, it's not as linear as it appears here. What happens is, if you look in the left, sometimes a react or a product that is created from a chemical reaction in step 1 can fly all the way to chemical reaction in step 4. And from 4, it can fly all the way to 2. So you have to take into account a massive system. And in order to do that, you have to use computational tools. So for my master's, I utilized something called Mass Toolbox. So it's like mass action stoichiometry something toolbox, in order to create a model that can look at photosynthesis. So why is this important? So if you look at the bottom, my motivation was to create a computational model of a photosystem metabolism for future metabolic engineering of diatoms, which are similar to plankton in the ocean. So think about it. If you can create a computational model and you can run tests on your computational simulation to see how can I maximize creating a useful byproduct. And you can change concentrations, change the irradiance, the photon levels of from the sun to maximize a byproduct that you want, then that would be great, because these diatoms and plankton are literally everywhere in the ocean. This would be endless energy. So, the implications for a work like this could be big. It's far from completion, and, I'm hoping someone else is carrying it over, but that's pretty much just the main idea of this. So what you see here are the different molecules from that photosynthetic pathway. So the first one is photosystem 2. The middle pathway is cytochrome B6F, and this right pathway is photosystem 1. I didn't write this backwards. It's actually 2 first and then 1 last. So what you see here are the different metabolites, and what you see here in the middle of those metabolites are different rate constants. So if any of you have taken general chemistry, you know that the rate of a reaction is dependent on the concentration of your reactants, as well as the rate constant that governs the speed of the reaction. So if you have you can have a 0 order reaction, 1st order reaction, it's all dependent on the number of molecules you have on the reactant side of your equation. So you can see how complicated this is. So it's a system, right? So if you see PQH here, where I'm circling my cursor, I don't know, this thing could fly all the way to the right, or it could fly to a reaction over here on photosystem 1. So there's no way humans can keep track of this. So what I did was I coded the physics and the chemistry of the biological mechanisms that occur in these chemical reactions. So what you can see here is just a very small portion of the code I wrote. the code's massive. But this is just a small code. So what you see here is I have the metabolite names, and then I also input like the different parameters on the right or on the bottom here. So you can see like I have the antenna size that catches sunlight, or I can even have, different irradiance numbers. So like the number of photons that hits a certain square meter of area. And there's a lot of math in here that's connecting it. But what you see here is on the right side is a very simple pathway of like a metabolic pathway. So you can see that sometimes, it's not linear. Sometimes it can be cyclical, and stuff in the end can fly to the very beginning. So the code I wrote was able to solve all of this stuff, like looking at a set of differential equations to determine the concentration of reactants and products. So if I go to the next page, so these results are from a paper by Kroon and Toms, where they're looking at the irradiance level. So like how the brightness of the sunlight, right? The number of photons, and PE is basically your photosynthetic rate. So if you want to increase, like, let's just say I want to create a biofuel molecule, like maybe the rate of photosynthesis is proportional to that. And you can see that even if you increase irradiance to a certain level, you start to plateau. So it's almost like it doesn't even matter if you hit 2,000 micromolars of photons per meter squared per second. Like you can see that there is a certain cutoff. So systems biology allows you to make inferences about these very complicated systems, and you can simplify it into graphical forms like these. So this is the model from Kroon and Toms, and using the code I wrote on the, oh no, that's not it. Over here, you can see that the results I got matched theirs. When I saw this, I was like, oh dude, I was so happy. You guys have no idea. It was great. So there are also a bunch of other things I looked at in this model. So for example, this master's thesis was like 88 pages. I'm not going to put everything here, but I think this was like one of the main figures that I really wanted to share, because it just shows you that even though you have a very complicated system with computational, like firepower, you can like sort it out and see trends. So what you see here is like these different lines is like if I'm affecting the ferredoxin oxidation rate constant. So if I change it from 0.15 milliseconds per millisecond to 150 per millisecond, you can see that my rate of photosynthesis would increase maybe about 2.5-fold. And that's pretty cool to see, because that tells the person who might want to make more biofuels, like, hey, find a way to increase the rate constant of ferredoxin oxidation. So yeah, very, very cool stuff. And also during my master's, I want to bring this up because I think this was a turning point which made me know for certain what I wanted to pursue. So while I was doing my master's at UCSD, I was also involved in the UCSD Technology Management and Entrepreneurism program. So this is a joint program between the UCSD Jacobs School of Engineering and the UCSD Rady School of Management. So this is between engineering, the business school. I took a bunch of classes and workshops with MBA students, and we learned the basics of business, how to bring a product to market, how to pitch ideas to investors, advertising, pricing, all of that stuff. At the end of this program, I was able to, we got this certificate. So, I'm a fellow in technology management and entrepreneurism at UCSD in the Rady School of Management and Jacobs School. For me, the reason why this made me want to pursue a master or a PhD, I'll explain on the next slide. But basically, it opened up a lot of possibilities. So for example, the possible paths from a PhD, maybe I can license a product. So if I'm creating something here and inventing something, engineering, you have to discover something, then you got to invent something to manipulate it. So we have to literally create something. And that's where, it gets really hard. But if I've seen it done at UCSD and PhD students at other schools where they've licensed the product from their work, And some of them have even like started up companies, have become CEO of their own companies and all of that. So to me, this was very appealing. This is where I was like, okay, I think I know where I want to go. So applying for PhD programs is a very big decision. So as opposed to master's degrees, which are 1 to 2 years, PhDs at the minimum, you know, here at Columbia in my department, it's like 5.5 years. My roommate took 8 years in electrical engineering here at Columbia. I think that's an outlier. I hope I don't take 8 years. I also want to explain why I'm pursuing a PhD, because a lot of people have asked me, like, why are you going back to a PhD after working at Illumina and doing your master's? Well, for example, for me, I think this is the best time to take risks. So if I want to go start a company, create a product, and do all of that stuff, I can't do that with a 9-to-5 job. And also, since I'm working with, you know, biomedicine, I'm not a computer scientist, so I can't create an app in my garage. I literally need access to stuff like, you know, the microscope systems here, all of the other Columbia tools and all of that. So to me, it was like, okay, there's no choice. But if I want flexibility to create my own thing, I need to use university resources. And this is why I'm pursuing a PhD, because I've seen people do that. And I've seen people jump into business afterwards and who are like trailblazers in their path because of that. The likelihood of this happening is very small, but you know, got to do what you got to do, YOLO. So I think it's important to take risks, calculated risks. And if it doesn't work out, then, you know, I can apply for other jobs. I feel like there's no downside to getting a PhD, especially, you know, before other of life's responsibilities. So if you want to apply for a PhD, research experience is required. Highly, like, I think it's required for a PhD. It's almost like if you don't have any research experience, you probably won't get in. So the best way to do that is to do research, whether you're in industry or an undergrad, because it's different, where it's like, if you're an undergrad, your professors and TAs have the answer to all your questions. But for a PhD, it's like, I can ask anyone on my floor, how do I do this? And everyone will say, I have no clue. So you got to figure stuff out. So the requirements for a PhD is you need to know the field of study, and you also have to invent or discover something of significance in the field of study that's never been found before. So now I'm going to jump into my PhD work. It's a little hefty, but now I'm just going to go very briefly through it. I'm not going to go into too much of the math, but I do want to show some of the cool stuff that I've done in my PhD. Real quick, before I start, I just want to say that I've been fortunate enough to be working with Honda on this project. So finding, you know, a big company like that to, you know, already say, hey, we need this, is pretty cool, because, you know, now the thing I'm working on, I know is a need for a big company, as opposed to creating something and finding a need for, you know, people to find it. It's like, this is definitely a need. And that is why, you know, I ideally wanted this position where I could do research, but research that could possibly have very fast turnaround times where the impact can be seen quickly. So hopefully this work will make cars safer for pedestrians and occupants, you know, in the next 5 or 10 years. So the title of my talk is Simulating Cerebral Edema and Delayed Fatality After Traumatic Brain Injury Using Triphasic Swelling Biomechanics. It's a mouthful, but we'll take it step by step. So introduction, finite element methods are used in the aid in the design of car safety systems. So what I mean by that is, I'll explain the concepts of finite element. Not everyone knows what that is, but it's a pretty cool mathematical and engineering technique that engineers and scientists use to, you know, do tests on objects before they even create the object. So the problem is that current finite element methods do not incorporate mortality due to delayed effects of brain injury. So for example, when people get involved in car accidents, not everyone's going to die at the moment of impact. Some people die a day later, 3 days later. So when you see those TV commercials of people doing tests on crash test dummies, how can you honestly look at a crash test dummy and say that dummy's going to die 3 days later? You can't. Biology is too difficult. So the purpose of this project is to simulate, those secondary mechanisms after the initial traffic accident insult. And a lot of these people die from the cerebral edema, which is brain swelling. So brain swelling happens and actually is responsible for a lot of deaths in cases in the ICU after car accident. In my model, I'm trying to make it as realistic as possible. So I'm trying to model ischemia as well. Ischemia is lack of blood flow to the brain. So in order to do that, me and the people I'm working with, my undergrad, Leanne, and several other professors, we're trying to find ways to model the lack of blood flow to the brain using this tool that I will show you guys. So basically the turn of events that causes death is you have brain swelling from the initial impact. This causes high intracranial pressure because the brain is a rigid volume. Your brain swells, the volume doesn't change, therefore pressure increases. This causes ischemia because certain parts of the brain, when they swell, they will squeeze adjacent parts of the brain. Then that restricts blood flow. Therefore, those parts of the brain will die. This causes cell death, additional brain swelling, and then eventually the person dies. So this is the problem I'm trying to address, and hopefully one day it can save lives down the future. So what you're seeing here is clinical data from Balistreri showing that as intracranial pressure increases, the predicted mortality increases. So you can see after 20 millimeters of mercury, like the chances of dying increase greatly. So this is what we're trying to address. And this happens after a car accident, like a day or a few days after. So once again, to reiterate, so you guys aren't lost and not bored, the problem is that cerebral edema or brain swelling may occur hours or days after a car accident, and current automobile safety systems are designed without taking into account this delayed effect. Therefore, my research objective is to model post-traumatic cerebral edema and the subsequent mortality due to swelling in order to assist with car safety engineering that considers edema. So people are probably wondering, what is finite element modeling? So basically, finite element modeling, so first bullet point, allows for mechanical testing before making the actual product. So for example, if civil engineers want to make a bridge, right, that's connecting two islands, you don't want to build a bridge and then go like, all right, we spent $50 million on it. Let's test it now. Let's put cars and see if it falls. You don't want to do that. Likewise, you don't want people to create a plane and go like, oh, let's create a plane. Oh, let's test it. Let's put people in there. No, it's a waste of time and money. So what finite element method is, for example, you see this car, you discretize your object into a bunch of small elements. So you see like little cubes here, little trapezoids, you discretize it. And then from that, you can see the effect of each element on its adjacent element. So if there's a deformation, if there's a force imparted on one element, it will transfer to the next element. And there's a lot of math in it. There's a lot of like linear algebra, all of that stuff. But we won't dive into that. But basically, that's the main idea. So it's like, if I want to test a car before I build it, I can test it in a computational environment. That's the goal. So what am I doing? Well, I'm trying to model swelling of the brain, so that delayed effect after a car accident, using FE-Bio. So FE-Bio is a tool created here at Columbia and the University of Utah in the mechanical engineering department. So FE-Bio is just a finite element framework designed for computational solid biomechanics analysis. So the Global Human Body Models Consortium, GHBMC, is just a company of 7 different car companies who have come together to create these brain models to try to make cars safer, so that car companies can do research and make, safety adjustments on seat belts and airbags. So my nodal displacements for the brain from different impact simulations, like side impact, front impact, they're provided by Honda. What you see here is a whole brain mesh, and what you see here is a cross-sectional brain mesh in FE-Bio. So before I dive in, let me show you guys like some of my work. That's the cool thing about computational work, is I can literally just show you. So what you see here is a model of the brain in a pedestrian severe accident. So if I zoom this picture out, I can actually look at, this one. So I can look at the amount of damage. So you see these variables, I can look at Lagrange strain, first principle Lagrange strain, deviatoric principle Lagrange strain, initial position. So if I look at damage, like cumulative damage, I can play it. So every second you see here, every time point is a millisecond in a car accident. So this is a person getting hit by a car right now. So if I zoom out, it's super slow, but you can see that the car has already hit the person's body and the head of the person is already falling towards the hood of the car or the sidewalk or whatever. And you can see that if I zoom in, so if I zoom into this picture, you can already see like the damaged areas on the brain. So if I pause it, I can already like take a look at where the parts of the brain there's a lot of damage. So you can see like at the top of the cerebrum, right under the bridging veins, and there's a lot of damage. So the goal is to translate this now into, okay, now that we see this type of damage, how do you possibly model swelling that can occur a day later or 3 days later? Well, glad you asked. You can use a lot of math and biology and physics. So what you see here is actually the swelling that occurs from that initial impact. So if I look at relative volume and I play this, you can see the brain starts to swell. So, So if I can even show like the skull. So if I show you the skull covers it, I do a planar cut and you can see the brain expanding until it hits the inside of the skull. And that's when your intracranial pressure increases. What you see here, these red areas are parts of the brain that swell. And I will explain how we go from the initial impact to the swelling that occurs days later. It's pretty wild. So now we're going to go into a little bit of the math and just the biology. So for example, what you see here on the left is a normal brain cell or maybe normal brain tissue. What you see here is that the sodium-potassium pumps leave a net positive charge into the external environment. So there are more cations in the extracellular space. And this is because your sodium-potassium pumps on the membrane of your cell are pumping out cations into the environment. As a result, you have an underhydrated, negatively charged matrix in the inside of the cell. And what you see here are negatively charged spheres. So these are representative of huge negatively charged tethered macromolecules such as DNA, glycosaminoglycans, just a bunch of other large proteins and macromolecules. What you see here on the right is that as you lose blood, so from an ischemic event, when there's lack of blood flow to the brain, or if there's a perforation in the cell membrane, you start to have your cations rush into the inside of the cell. And this is because the cations are trying to go to the negatively charged fixed charge densities. What this does is it makes the interior of the cell more, have a higher concentration. So it's like what the cell is trying to do is trying to counteract that higher concentration inside the cell. So what it does is it will start to swell so that the concentration of particles on the outside of the cell and the inside of the cell stay the same. So you can see that this is like the biological effect of swelling, or at least the theory. And the difference in osmotic pressure, and take note that it's the difference in pressure that is driving the fluid into the cell, can be given by this equation here, where you have R as the gas constant, ideal gas constant, theta is temperature, CF is your density of your negatively charged particles, and your P and your P asterisk are just your different osmotic pressures on the inside and outside of the cell. So quick modeling overview. I'm trying to go from a car crash scenario up here with an initial input, 50-kilometer crash or 70-kilometer crash head on, all of this stuff. I get the displacements. I obtain a maximum principal strain from those displacements. I then convert those to cell death. assuming that cells release more of that fixed charge density, those negative spheres as they die. Then I simulate swelling using FEBio, and then I model ischemia and cell death, and then I simulate again, calculate ICP by taking the volume average third principal stress, and then I predict percent mortality by comparing this to the clinical data from Balistreri et al. So what you see here is just a curve that my advisor and I have made. We just picked this curve as the best fit curve to try to match the actual clinical data. So what you see here is ICP, so intracranial pressure following an impact. So you can see that the brain starts to swell. So this is the model I created now, right? This took forever to build. Oh man. So what you see here is if I take the volume average third principal stress, basically like the compressive pressures, I can say that this person has an 81% chance of death. If I take into account the ischemic results, so if I take into account the areas of blood, areas where the blood doesn't flow, there's a lot of math in that too. There's a lot of MATLAB calculations. So I can say that those areas of the brain die, so therefore they should start to swell. And you can see that this person has a 99% chance of death. So this was from a database where the pedestrian actually died and had like, actually, they actually passed away. So what you can see here is just the overview of the process. You have the uninjured state on the left. You have swelling after impact in the middle. And you can see that your pressure, your third principal stresses, volume average third principal stresses start to increase at this point. So I'm probably around 5 kilopascals on average. When I move here, I have swelling after the impact and ischemia. And you can see that now I'm in the orange part, so like 12 kilopascals. And you can even see that these white areas, so these are the ventricles of the brain where the cerebral spinal fluid usually stays, which is important for cushioning the brain. You can see that they start to get compressed because fluid starts to leave because they're becoming displaced by the solid matrix. So basically, this work is just the impact of it so far is I showed feasibility of modeling delayed brain swelling after an accident. So far, I've looked in the literature and it doesn't seem like anyone in the world has done this yet, which is good. And so far, I've been able to predict likelihood of death based on brain deformation. So on the first 200 milliseconds of an impact, what will be the outcome of a person 3 days later? With this, I hope to assist and influence design of safety systems in a computational environment. And for future work, I hope to incorporate hemorrhage because the presence of hemorrhage of blood in the brain has a high mortality rate. And I also want to validate the model because the model is only as good as the material properties you put in it. So my next step is to actually do like tests back there to look at stress and strain of brain tissue and to actually put those in this model. So that's probably my future work, 2021, 2022. That's the next step. I want to acknowledge all of these, Columbia Engineering, my lab, this lab in mechanical engineering, and also Honda. Before I end, I just want to show you guys the math. It's pretty nuts. So I'm leaving all of these out, but there's a lot of math on chemistry and biochemistry. So that you can see vector calc is necessary. So we have J, which is like your volume ratio after deformation and swelling. You have divergence. You have a bunch of stuff. Now you're looking at different charges and you're looking at like bulk modulus and all of that. So, all of this is very important. Like we're also looking at different material properties. So the math gets very intense. Yeah, this looks really scary, but got to do it. So if we just go back here, I just want to show you guys real quick that you can actually see the brain like starting to like during its swelling. And this will be my last thing I bring up just so we're not short on time. But if I want to look at different cuts and if I want to make this 0, I can look, at sagittal planes, coronal planes, frontal planes. And I can look at different parts of the brain too, because I have a bunch of materials here. So it's pretty cool model. This was difficult to make, but we out here, we're getting there. So yeah, summary real quick. If you want a job after graduation, now I'm trying to go back to the high schoolers and middle schoolers in my talk. Do internships at college, especially at the end of third year. Treat your application like a full-time job. Tailor your resume for every position. What people don't realize is that it's hard. Like for me, I did get into all the major biotech companies as an engineer, but people don't see the 80 or 90 rejections I got. So you got to move fast. It's like, I don't care about those 80 or 90. What I care about is like those solid 10, like Genentech and all that I got. But, there's a lot of failure that happens, but just keep moving forward, like take action. Also, put skills from internships and courses in your resume. Their courses are important. Like don't, throw that off. Go to career fairs. And if you don't have time to talk to everyone, put your resume in the pile. It works. Also, your lab research internships are still effective for applying to industry. Don't think like, oh, I don't have industry experience from undergrad. How can I apply for an industry job? Doesn't matter. You're just trying to translate your skill set. And if you want to go to grad school for a master's, you don't necessarily need research experience, but if you want to do a PhD, 100% you need it. And also get letters of recs from class instructors, work supervisors, especially professors in lab. These have the heaviest weight because these are researchers. That concludes my presentation. Thank you. I hope I hit the time limit, but if anyone has questions, feel free. So yeah, I try to address everyone, the variety of people in this talk. So hope you liked it.
Thank you so much, Andrew, for that interesting and super inspirational talk. I think, as you mentioned, for a lot of different ages and for anybody listening in. We hope it was really educational for all of you, whether you're tuning in from an undergrad perspective or much younger, and whether you're already interested in this research in biomedical engineering or just exploring STEM right now. And next up, we actually have a couple of questions for Andrew that have been curated by our speaker series team. And we hope this will give a little bit more insight on his journey in STEM as well as his research. And so I guess we'll start off with, Andrew, I know you mentioned a lot about sort of your undergrad journey, but what was your first interest in STEM? How did you first get interested in not only just the medical field, but was there any sort of like teacher or event that sparked this interest and made you particularly interested in, for example, how you mentioned approaching medicine in the beginning and then shifting towards biomedical engineering?
Yeah. So honestly, I would say for the first part, it came from my parents. Like very initially, I know my parents, my mom did electrical engineering. My dad did aerospace engineering. He did his PhD in aerospace engineering. And to me, that was already cool. Like they would come home from work, they would bring stickers of like rockets, like planets and all that. So to me, that was already like instilled a sense of wonder in me. So I would say it started from that young age. And then as I moved to like middle school, so like 6th grade, 7th grade, 8th grade, like my science classes, so like earth science, physical science, biology and life science, those are super interesting to me. But so were the math classes and chemistry, and honestly, every subject related to science. So it was also my middle school teachers who helped lay that foundation. So my algebra 1 middle school teacher, as well as my physical science teacher in 8th grade, they told me like, oh, Andrew, like you seem really interested in this stuff. You should pursue it. And to me, it was like, yeah, that sounds like a great idea. Why not? And to me, I wanted to get involved in it. Like, I just loved how math, physics, and chemistry all work together. The reason I chose biomedical engineering specifically is because I wanted to integrate my interests into specifically addressing human health. And that's because I think addressing human health, it's like, you can do any job, any career to impact people and their life. But I feel like when you're addressing human health, it's more like you're addressing like almost the core of the patient, like the person, like all these jobs, all of them, all positions, all equal impact, all equal dignity. But for me, it's just, I wanted to be like, meet the patient where they're at, but still work with innovation. So for me, that's how it started. And that's how it's still continuing to this day. I know I do want to maintain my, my technical skills, but I do want to also get into entrepreneurship and business. So that's the next step. So right now, I want to maximize the technical skills. Next will be to maximize the leadership and business skills, and then maybe 10 years, 15 years later, put them together. So yeah, just keep learning, I guess. That's it.
Absolutely. I think that echoes with a lot of students who are, looking to go into higher education or even just interested in a lot of subjects. So I think that's really cool to hear about. Another question is more targeted towards those students in high school and undergrad especially. But were there any activities such as clubs, sports, student government, STEM clubs, or even research? I know you've already mentioned research, but anything in particular during your undergrad experience that really helped you during your future and your job process and application to grad school process?
Yeah, so pretty funny. Specifically for me, I wasn't involved in too many clubs that were related to, this kind of stuff like STEM, or now I'm trying to think back. I think most of my time was really hands-on stuff, like in the lab, like just going into lab and just doing research. I think if I joined clubs, I would have seen more, like, bigger horizons. I would have seen people, do their work, and I would have been maybe inspired. But for me, I really just heavily dived into the lab work, whether it was a wet lab. Actually, it was all wet lab in undergrad. Now it's, more computational. For me, yeah, it's not the best answer I'm saying, because I wasn't really involved in any of those like STEM clubs. But I can say, in hindsight, that I think it's a good idea to join those clubs where, that are like engineering clubs or, biology clubs or pre-med clubs, because it is in those groups where you'll find your friends, people you really enjoy hanging out, like people you can have fun with, because having fun is important, right? That's, one of the most important things. But you also have people who you can share ideas with. So I would recommend to high schoolers and people in undergrad to, prioritize the work and the research and the internships, but also see if you can make time to foster those relationships in these clubs. Yeah.
Yeah, I think you've given a lot of sort of advice about, like, pursuing STEM as a whole. It's very unclear often what students are interested in, even as undergrads, for example, or even past that. People don't always know exactly the path going forward. So I think it's really awesome to hear about how you navigated that journey, and students are really excited to hear about that as well. We actually want to open up the Q&A to the audience now. So just to give a couple of guidelines really quickly, in order if anybody from the audience wants to ask a question, please use the participants tab in the bottom and just raise your hand. We'll do our best as hosts to sort of look through and make sure we call on those people who have their hands raised, and you'll be able to unmute yourself, turn on your video, that kind of thing, if you actually ask a question. Just a reminder that the session is still being recorded and live streamed on YouTube. So if you unmute yourself or sort of turn on the video, just remember that is still occurring. And another piece is, if you'd like to ask an anonymous question and aren't able to turn on your audio or video for any reason, please feel free to just message me through the Zoom chat any question that you have you'd like to ask, and I will also do my best to ask that in the order that they come as well. And for those of you who are tuning in via the YouTube live stream, you can also ask questions in the comments panel on the right-hand side as well. So I'll start opening it up right now, and for anybody with any questions, please feel free to raise your hand in the participants tab.
Don't be shy.
I guess while people are still prepping their questions, one thing I'd like to ask is, did you find anything to be the most difficult part of your sort of undergrad journey or decision to either go into industry versus making that decision between going into I guess, further research and like pursuing another degree? Was there any piece that was really difficult to you?
Oh yeah. Oh yes. So I think my mom and dad are watching too. They know this. So in my talk where I said like I originally wanted to do medical school, I was preparing my whole undergrad for that. And I remember when people would ask me like, why do you want to do medical school? I would tell myself, oh, I want to help people. You can help people in many ways, honestly, right? You can build a bridge, you can design cars and all that. For me, I realized I was like really conflicted because when I was going to these talks and just seeing on YouTube of people like making innovations in medicine, like medical devices, I was like, oh, that is so cool. But I feel like I can only do that if I'm more focused on, going to the grad school or going to the industry. So I remember telling my parents, I was like, yeah, I don't think I'm going to apply for medical school this year. And I remember they were like, oh, okay, I guess that was your plan the whole time, right? And then I told them, yeah, but the bioengineering, it's such a wide variety of stuff you can do. And I remember I did feel clueless a little bit after graduating. And I was like, dude, I have no idea what I need to do. And my mom and dad straight up said, first things first, find a job. So I was like, okay, I guess I can find a job because I can always think about what I need to do while I have a job. So that's when I started, right when I finished fourth year of college is when I just started applying for jobs. So I didn't follow my advice applying early, I applied late. And I remember that was the most difficult part because I was switching from my original plan and I didn't know what to do. I was conflicted between med school, industry, and going into graduate school. And to me, it was tough because it was like, oh man, now I'm unsure. People are getting to med school, people are getting into these big companies. And for me, I didn't know what to do. But I think the most important thing I found from that is to be okay with switching career paths. And it'll all become a benefit because as broad as the experiences were, like doing photosynthesis, traumatic brain injury, cancer research, drug delivery, working with DNA sequencers, it's so different, but I can bring them together for a unique perspective. And that's where where the thing that scared me the most at first allowed me to talk to chemists at work, allowed me to talk to software engineers at work, allowed me to talk to electrical engineers designing circuits, allowed me to talk to mechanical engineers designing the gears and looking at the physics of the gears. So all of it came together where I was like, wow, you know what? Like, even though it seemed like chaos and it was a very painful moment, now that I look back, it's like, it's allowed me to, it's like shined light onto all of the moving aspects of a bunch of different scientific fields. And I think, yes, that was a very painful time. And that, to answer your question, that was me where I was like, I don't know what to do. And I delayed my path a lot. But in the end, I think, it works out if you keep taking the next best step, move to the next spot, and then just point your arrow. And that's what I was trying to do. So.
Sure. One question from Alyssa, I believe. Let me scroll through it really quickly. It is, how do you deal with imposter syndrome if you deal with it at all?
Yeah. So, oh man, I think everyone has imposter syndrome. So yeah, this PhD has been such a humbling experience. I'll just straight up say it is hard. It is really hard, especially here. It's really hard. But, at the same time, there have been many times where like I mess up an experiment or I don't understand the thing I'm coding, or I don't understand like, oh, how do I even move this microscope? Or I hear my advisor and other grad students talk, and it's like, oh, they really know their stuff. I think what's helped me is to just remember to be, I'm talking to myself too, is to remind myself to be humble in all of this, because being humble allows people to be molded by, like their advisor and other grad students. So yeah, there are people who I met, it's like, man, how do they know this stuff? But at the same time, you know, I know stuff they don't know, and they actually go through the same thing. Everyone goes like, dude, I don't even know what I'm doing, but other people say the same thing. And it's like, everyone's basically, you know, going through the same hardship. And to me, that's that's been kind of comforting. And it's also realizing that whatever failures I've been encountering and whatever like things that look like common sense that I don't understand, I need to realize that people have been experiencing that. Like the brightest people I know, some of the brightest like postdocs and professors, like the only reason they're good at this is because they weren't good at it at first, right? So to deal with imposter syndrome, I do that. I honestly do that, and I pray and I just move forward. And I try to learn from every experience, because there's a lot of times like I get pushed down to the ground because it's like, wow, I don't understand this. But yeah, persistence.
A question, also that was a great answer. I think that's sort of like a motivational piece that we all needed. A question from Julia is, what has kept you motivated through your educational journey?
Yeah, so I would say I would say at a certain point, motivation isn't as powerful anymore. So I would say at first, it is motivating to say like, yes, I want to go to lab. It wakes me up. But let's be honest, I think, you know, doing the work, you know, everyone's job, I don't think they wake up happy like, oh, this is going to be a great day, like every day. So it comes down to discipline at that point, meaning like persistence and discipline, where it's like, for example, if someone doesn't want to go to the gym because they don't feel like it, but they still decide to go, they use their free will to choose. I think it's the same as saying like, let me assess the odds. Like, do I not want to go because, you know, it's a bad environment? Then, okay, that's important. Then maybe take that into account and back away from what you're doing, like leave the job. Or is it the job is great, but it's just difficult and I don't know how to do it, but I love it? If it's the latter, then I think it's important to just keep at it and stepping away once in a while, because sometimes things work when you're like, you know, when you're just cooking dinner or like showering, you're like, oh, I think I found out what to do next. So yeah, basically motivation, don't expect that to last, you know, forever. I think it you know, it's like an asymptote. It exists, but it starts decreasing until maybe the next breakthrough. But I think it's discipline to just keep sticking it through that makes people that, you know, that's helped me keep going. Not saying I'm perfectly disciplined. I'm just saying that, you know, I think it's what helps everyone keep going. Yeah.
It looks like, I don't know exactly what the name is here, but B1 has a question, or at least raised hand. So feel free to unmute yourself and turn on your video.
Hi, Andrew. You guys hear me?
Yeah, I can hear you.
Okay. My question for you is, how did you pursue your area of research in traumatic brain injury,
Yeah.
you know, through your master's or PhD, and you know, what influences did you have to specifically choose that area of research?
Yeah. So, okay, this is important. I forgot to mention this. So when you apply for a PhD, right, I'll go into my story. When you apply for a PhD, you do want to have an area of expertise or an area that you want to work with. So for me, I remember when I did my master's degree, I found that entrepreneurship program for like grad students. And, you know, I've seen examples of people start companies and lead companies from their PhD work. So for me, the way I got into traumatic brain injury was I wanted to find work that had high impact, meaning there was a huge need for it. So like, it'd be, maybe I can work on something that's super cool, but honestly, no one would really care. But for traumatic brain injury, what I liked about it is like, this is an $80 billion per year problem. Everyone has concussions. This affects the automotive industry. You know, this affects like sports, right? Football and all that. So it's such a big problem where you can see the need because of the cost. And to me, that's what stuck out to me. Like it stood out. And it was either between this or, some other kind of like cancer research and all that. But to me, I wanted to work with this because I really like physics and mechanical stuff. And to me, this was the perfect mesh of my interests, but also the need it had, because Honda wanted me to work on this, or they wanted the lab to work on this. So I was already told myself, okay, Honda wants to work with us. I don't even have to like look for people. So I prioritized interest as well as the potential impact, like by looking at the cost of the problem that it's addressing. I hope that answers the question.
Yeah, thank you.
Yeah.
We actually have two pretty similar questions from Joe Marie and another participant. One of them was, as you go through your PhD program and generally navigate through life with everything going on, how do you practice self-care? And the flip side to that as well is, with a very hectic schedule, how do you balance your life, time with your career, friends, and family?
Yeah. So, I would say it's important to put boundaries. What I like to do is, like when I align my day, first thing I wake up, eat breakfast, pray. To me, that's important. It aligns my day, honestly. It helps me know what I need to do next. And to me, I put boundaries. When I say boundaries, it's like I will have a scheduled gym time, scheduled like time to hang out with friends, or scheduled time to like practice piano. And in order to make that work, I will go like, okay, that means I have to sleep early 2 days in advance. Like I'll plan it ahead of time. Obviously, things can go wrong and, things can arise from nowhere. But for the most part, a lot of it can be done with placing boundaries. And what I mean by that is like, if I go in a lab, it's like, I don't want to just sit in lab forever, like for 12 hours, when I can say, okay, I'm going to make this the most productive 6 hours possible, right? It's not the length of time, it's the density of the time. And I like to keep that keep that in mind, where it's like, I will split my day into different chunks. So like, okay, lunchtime, I'll go to the gym. And then in the evening, like I'll hang out with friends and all that. And this time will be for study time. But I try to not extend too long, because honestly, no one's studying for 12 hours. If they're studying for 12 hours in the library, they're lying. It's honestly only 4 hours of intense studying. The rest of it's Instagram. So I would say a lot of it is just being intense in the moment where you're at, intense in terms of the rest you're getting, intense in terms of hanging out with friends, intense in terms of like just doing leisurely activities and just being in that moment, because like, multitasking doesn't really work. So for self-care, I would, to answer the self-care, I think that was a scheduling thing. Now to answer the self-care, I would say I just like to do things that I simply enjoy doing. I try my best to make time for it. Obviously, that doesn't work all the time because life happens. But a lot of the times I like to prioritize the sleep, because if I don't sleep, I'm groggy and everything else falls. So a healthy diet and good sleep is what I like to prioritize. For other self-care, yeah, I really try to make time for friends and hanging out with them. Sometimes when the workload is heavy and, thank goodness I'm done with classes, but let's just say I had a bunch of classes. There was be some times, maybe like if I'm doing my PhD qualification exam, I have to hide for 5 months. But then it's like after that 5 months, then, I can like hang out a little more. So that's how I would say I balance. I try to put full intent into the hangout or the sleep or all that stuff. Because, it's too easy to get distracted and say like, oh, I'm going to sleep. But like me, like I need to work on this. Like if I'm on Instagram and it's like, oh, I just lost an hour of sleep. So yeah, just having intent in the moment, that helps a lot. You'd be surprised.
Another question from Evangeline is, how do you deal with frustrations or rejections?
Yeah. Oh, this happens all the time. So for the past 6 months of my PhD, I've been trying to work on this certain thing and getting it to work. And there's small steps moving forward, but it hasn't really worked. But the good thing about research is it's breakthroughs. So it's like sometimes you don't see a breakthrough and then all of a sudden 9 months later, boom, or something. So for me, I try to just keep, knowing the truth that if I stop, it'll never get, like if I step away completely, then it'll never get done. But at the same time, I take confidence in knowing that, this work is important, or hopefully if it works, it's important. If it doesn't, then, but I take, like what keeps me going is, my friends and family. And also, like I said, like I pray like for the confidence to like stick things through, which has helped a lot. Honestly, it's like, if I didn't have that, I probably would have like given up a long time ago, but it helped. All of those things put together have really allowed me to keep going when times get tough. And I know everyone has tough times. Everyone has their own share of difficulties, but I think it's important to never be discouraged or despair. Like it's good to step back. It's even good to like take a break for a week maybe, but I think it's vital to never lose hope. So when I deal with those rejections, I step back for a little bit and then I get back into it after I'm done. So there's a lot of failures. And yeah.
Absolutely. This is actually a combination of a couple of different questions, so I'll try to phrase it in the best way that I can. A couple of people have asked, how would you recommend, if you're interested in computational biology, how would you recommend getting into it? Where can I learn more about FEA? And sort of just resources for anybody interested in learning more about the field. For example, books or open courseware, that kind of thing. Do you have any recommendations?
Yeah, so the field of computational biology is huge, right? There's like what I worked on, systems biology, right? Systems biology in itself is massive. There's people who are looking at, trying to work on engineering bacteria to like, trying to find ways like discover new antibiotics to like kill bacteria that are like resistant to antibiotics. Or like my work, the photosynthesis stuff, I would say if you're interested in looking at computational biology, if you're a college student, you'd be surprised. Just type in your current school and type computational biology. So let's just say, I don't know, UCSD, type computational biology. There will be several labs that pop up, like almost guaranteed. I would also say, like, if you want to learn more about other computational stuff like finite element method, there's a lot of books out there, but maybe just watch a YouTube intro video at first, because you don't really have to like dive into all of the math. So I would say, yeah, YouTube helps. YouTube honestly has everything you need. And if you do want to get involved with it and you're at a university, I'm like almost certain, a professor or something is working on a computational biology problem of some sort. And you can just email them and tell them like, I'm interested in this work. I don't have experience. That's how it starts off. When I was an undergrad, I didn't have experience, got to start somewhere. So I didn't have experience and I just said, hey, I'm interested. Can I join? So yeah, don't be afraid to reach out to professors. That's important. YouTube, to answer the question, YouTube.
Another question related to sort of your work as a scientist and engineer is, how do you believe that scientists and engineers can better combat skeptics when discussing computational work? And on that note, how much more work has to be done in terms of making computational biology, for example, more accurate?
Yeah. So, yeah, I guess the only way to do that, because when I presented this work in Europe, in the Netherlands, and then the talk I was supposed to give in Germany got canceled a few months ago. Whenever I give talks on this, I get questioned all the time. So like, when you do stuff in a computational environment, obviously there's so many more variables in real life, right? So for example, when I'm looking at these computational models of car accidents, we're looking at a database of car accidents, but how do people even know how fast the car was going at a certain crash? What do? They measure the tire tracks, the skid marks, the type of damage in the car. So there's too many uncertainties. Another issue with computational biology is that, what if all the stuff I'm encoding is not all the variables that are present? Unfortunately, that is, that's something needs to be addressed. So when people ask me during my talk last year in the Netherlands, like, how can you add more credibility to computational models? Well, number one, you can do experiments to validate them. So my next step starting January will be to start validating this model, start actually testing real brain tissue from real people, and hopefully, maybe, and then be able to, do experiments to test the parameters and put those in the computer. All that can do is add more credibility to the model, but obviously it'll never be as perfect as real life. But you have to realize there's a trade-off, right? If you don't do this in a computational model, how else are you going to do it? Like, you can't crash people. You can't say, hey, crash test dummies only go so far. We need to get volunteers for a crash. Like, there's no way. So sometimes this is the only way to do stuff. And in order to move forward, it at least shines light on what the next thing needs to be done. I think that answers the question for how to, the skeptics. I forgot the other question was, but I hope that answered it. I think I answered the second one.
Yeah, I think you did as well.
Okay.
I guess last question for you is a little bit more about your future. But what do you think you'll be planning to do after you complete your PhD? And I know you've mentioned a little bit about business, but what are you looking forward to then?
Yeah, so I hope this is not wishful thinking, but I've summarized what I really want to do in one sentence. It's broad, so it can take shape, in a bunch of different ways. So my vision is to integrate science, medicine, engineering, and technical entrepreneurship in order to lead medical innovation. So whether that means licensing a product to a big company, whether that means coming up with a startup company, whether that means leading a sector of a big company, like an established company already, whatever it looks like, whether it's pharmaceuticals, medical devices, any of that, I want to, I just want to lead a medical effort, whatever that looks like. So after the PhD, I would say, I have to be aware that anything can change, anything can happen. Ideally, I do want to dive, maybe see if there's possibilities with, starting something like, I don't know, a company, if that's even possible. If not, maybe, starting off as like a high-level engineer at a company, or even getting into consulting, because what I've seen from a lot of PhD graduates in this department in biomedical engineering is they get into consulting and they start like building up their like business skills and their knowledge and their leadership skills. And to me, that seems like a really cool idea. So all I can say is I'm open, but in the end, I really want to say, whether that end is 15 years from now, 5 years, 10 years, I just want to say that I am leading medical innovation in a substantial way. I don't know where that'll go, but I'm hoping that the PhD, like if I, get into like entrepreneurship and starting something, I do hope that this PhD will add credibility, because especially if you're trying to start a company in like anything medical related, it's too hard without a PhD. Like if you're creating an app, it's easy. Like you can show your phone, see my app works. But how do you know that heart valve works? How do you know that trachea you're making works? How do you know that drug you're making actually lowers blood pressure? So there needs to be a level of credibility that's a little higher, because the responsibility, like the consequences could be a little more devastating. So yeah, I just want to lead medical innovation. That's all I got.
Awesome. Awesome. Thank you so much, Andrew, for all your answers and to all our questions. I would also like to thank everyone in the speaker series team that worked very hard. To make this webinar happen. There are Abigail, Bianca, Sristi, Zainab, Chloe, Angela, and me, Lola. And I would also like to thank Nikita, Sam, and Abby Lang for helping us with the marketing for this webinar. They're from the STEM Chats marketing team. And special reminders is please fill out the post-event survey, and please follow us on our socials. Subscribe to us on YouTube, where you can rewatch this live stream. And to do so, please scan the QR codes on the screen separately from your phone's camera, and you'll be directed to the post-event survey. That's it. Thank you so much, Andrew.
All right, thank you. Thanks everyone for planning and everyone for attending.